All right, and so are we recording now?
Yes, I just hit the record button there, just so everyone
Right,
is aware.
So I'll refrain from talking about my son for a moment, and we will start. So hi everyone. I want to thank everyone for coming to my talk, Universal, and that's Cross Homotopy cover for graphs. And so I want to start with giving some background on what we're going to be talking about. So she's with us today, Dr. Laura Skull, and this is all part of a general joint research, well, I want to say program that I'm doing with Laura down at Fort Lewis. And the general flavor of what we're doing is we're taking notions of homotopy from topology and we're trying to move them into graphs. And we want to do so in a way that's like natural and native to graphs. And what I mean by that is what we don't want to do is just take like a graph and treat it as a topological object, right? And then say, oh, do homotopy on that. Or take a graph associated with some topological object and say, okay, do homotopy with that topological thing. We wanted to talk about what homotopy looked like in a way as if it emerged within graphs, right? Without explicit reference to topology. Of course, using topology as a guide, right? But not, explicitly. And so the way that made the most sense to us to approach this is categorically, right? That whatever categorically happened within top should also happen within graphs. And of course, there have been some other people to look at this stuff, and so we followed down the path that they began. And so, all right, I should note that I'm the graph theorist in this collaboration. I'm not a topologist, and what you see here, Laura is the actual topologist in this collaboration. Now, in particular, in this talk, we're going to be talking about covers, right? So we're going to be talking about covering spaces and universal covering spaces. If you're familiar with that from top, then that's good. If not, we won't need a lot of background there because we'll be talking about what these things look like in graphs anyway. All right, so again, some preliminary stuff. How do we want to move from topology where everything is fundamentally sort of continuous to a world like graphs where everything is fundamentally sort of discrete? There are certain things in topology that we need translating, right, to see what the mirror notions are in graphs. So first things first is, again, because our approach is categorical, what we want to talk about is what do the morphisms look like when we're in graphs, right? And so in topology, just very roughly speaking, the morphisms are continuous functions which preserve convergence. And so the structure that graphs have instead of being convergence, there's no, right, increasingly closeness to each other, it's fundamentally discrete. So what graphs have are adjacency, right? You have two things and they're either connected or they're not, right? And so that is the morphism in the world of graphs. We're interested in functions which preserve the adjacency. So here I have a map from the cycle to this path. And what we have is we're mapping 2 and 3 to the same vertex, 1 and 4 to these opposite vertices here. Can people see my cursor or no?
Yes.
Yes.
Okay, good. All right. And so, what that gives us then is that, right, 1, 2, 3 and 1 to 2 were adjacent before and they're adjacent afterwards, and same with 3, 4, 2, 4, right? So the adjacency is preserved. And so such a function of vertices is called a graph homomorphism, right? And that's going to be the morphisms of our category. And so we want to establish some familiar things too. So if we remember what it's like to do homotopy in topology, right, we usually take the space, cross it with an interval, right, and then define the homotopy in terms of the resulting object. So what do we mean by a product then. And so if we are, so people who are familiar with graph theory know that there are like a million different products, right, in graphs. And some of them I'm not 100% convinced should have the name product associated with it. A bunch of them are really just
in binary
operational two graphs, basically. Right? But the one we care about, again, because we're working categorically, is the tensor categorical product, right? So in topology, you get, if you have two spaces, the product is the Cartesian product of points with these projection maps, right? So that an open set here shoots down to these open intervals here. And what you have in graphs then is a similar object, right, whose vertex set is the Cartesian product of the vertices. But then what you have is, if I project down to this graph, or I project down here, right, either way, what you get is the appropriate projective morphism. So this edge, for example, goes to this loop. And this edge here goes to this loop, right, as things push left. As you push down, then all of the cross edges go to this edge here.
Are the graphs that you're using loops? Are they directed, finite?
Oh, so these are undirected, and they're not necessarily finite. Although most of our focus will be on finite graphs, they don't have to be. So this definition for incidence works perfectly fine.
And multiple edges allowed, or?
Oh, so right, so loops allowed, but only one edge between, at most one edge between a pair of vertices.
Okay.
Including the vertex in itself. So you can have one loop, but not two loops, right? And so what we're setting up is a binary relationship where, given any pair of vertices, right, either they're adjacent or not, right, and then there's not multiple loops or edges between them.
So is this notion of product just what you get categorically if you said, well, a product is a certain kind of pullback?
Yeah, exactly. So if you're in the world where you have but the single edge, right, or not, and then right you want to satisfy the UMP, right, that's that object, then right, this is exactly the rules for obtaining that graph.
And remind me, this is the classic definition of Cartesian product for graphs.
And this is no, actually this is the categorical product.
Okay, so
right.
this is a product that you're calling Cartesian, but what's called a Cartesian product is not.
So the vertices. So what I mean by the Cartesian product is that the vertex set is the Cartesian product of the vertex sets. Sorry.
Uh-huh.
But I'm pretty sure there is a separate product called the Cartesian product.
There is.
There is, right? And this is not it.
Oh, okay.
Yeah, I don't remember what it is.
Confusion cleared.
What's that?
Confusion cleared.
All right, thank you. I'm sure it's possibly the product in some weird category, but I haven't thought about it very much.
It's close. It's not the same thing, but anyway.
And so, right, so what we'll denote as an interval graph then is the graph IN, which is vertices from 0 to n, a path, each one of whom is looped. That's going to play the role of our interval that we would normally use in topology, right, to make our homotopy. And so, right,
Wait,
with all of these
why
changes,
should we regard that as playing a role of an interval?
Can I hold off on answering that for a second? It's because I think what you're trying to ask, if I can put words in your mouth, is why the loops, basically.
Yeah.
Right. And so we'll see that in just a second here, and I'll address that shortly. Right. So in topology, we have two functions are homotopic if you can sort of continuously transform one of the maps into the other, right? And so we have maybe 0, 2 cross with an interval, and then, right, if we restrict to the very top, we get this inclusion. If we restrict to the very bottom, we get this constant function, and then there's this continuous process. And so the sort of analogous thing that happens in graphs is, right, we take the original 0, 1, 2 path and we cross it with I1 and we get something like this, and you get a function that embeds here, and then we can fold down here. And so the reason we need that we're using I instead of P, so let me back up here, is because if you want to preserve, right, if I take the 0, 1 and I cross it with this, and I want my cross sections to look like the original 0, 1 graph, right, then I'm going to need there to be a loop here in order to have this edge, right, because 1 has to be adjacent to 1 in order for these to be adjacent, right? If I just have 0, 1 cross 0, 1, what you get is 0, 1, 0, 1, and not these cross edges. And then you don't get a slice of the target space, so to speak, at each section. I explained this. I was talking to a topologist at a joint meetings once, talking about what I did, and is very uncomfortable with the fact that products of connected graphs could be not connected. That made him very sad, as it should. And a group of Laura's students actually explored this idea further. I won't get too sidetracked with that at the moment.
Little loops are for the connectedness.
Right, so the loops are so that what you get, right, at each sort of layer is a copy of the original graph. Right, so if this is I1, but if I had P3 cross IN, then I would get a something like this continuing down.
So if I collapse,
I have a P3 here, P3 here, P3 here.
so if I think of this as an accordion and I collapse the top path with the bottom path, then it becomes P3, and if I collapse it horizontally, then it becomes I1.
That's correct, yes.
Without the loops.
Without
Okay.
the loops. And not just that, because that's not necessarily unique, but that at each of these levels, there is a subgraph that's isomorphic to P3. Right, so I get a P3 here, a P3 here, and I get as many P3s as I needed.
Okay.
All right.
So you're not doing Cartesian products with an arbitrary graph. It's only these interval ones that you're doing.
That's correct. Well, I mean, yes, that's the one we're primarily interested in. I mean, we will do other stuff, but that's the one we're primarily of interest. Correct.
Sorry.
All right, so we have a definition here for the exponential object in the category of graphs, and it's a fairly technical one. So it's kind of all right if we don't read that that theorem too deeply, and instead just focus on our example here. So what I have here is a graph G and a graph H, and over here is the exponential object, which describes the morphisms essentially from G to H. So what you have are that the vertices are all the possible vertex maps from G to H. And so, right, there's 2 vertices in G, and there's 3 targets, so there's naturally 9 possible vertex maps. So you get 9 vertices. And then you get an edge between a pair of vertex maps whenever you have an edge in G. F of V and G of W is an edge in H. Right. And so what happens, if I can ask the audience, if I replace this G here with an F?
missed
does
it.
anything of
Which
significance
G?
occur? Sorry, say again.
I missed it. Which G?
This G here. So instead of f of v, g of w, if I said, all right, whenever vw is in E of G, then f of v, f of w is in E of G, E of H, sorry.
That would be a homomorphism from G to H then, right?
That's correct, right? So a homomorphism is that would make f a homomorphism from G to H, right? A homomorphism is a function that says, all right, whenever two vertices are adjacent before, they're still adjacent afterwards, right? And so what you get then is that you have loops. Sorry, I didn't mean to do that just yet, but you have loops if and only if that particular vertex map is a homomorphism. So these four here are the four possible homomorphisms, right? 0 has to go to A or C, and then the 1 can go to either B or A or B or C, right? Depending where 0 lands. So that's your 4. And then these two have a connection between them. So for example, AA means they both go here. AB means, all right, 0 goes to A, and then 1 goes to B, 0 goes to B, so there's an edge there, and then similarly here. So you're homotopic if there's this looped path in the exponential object. Right, so like this guy here goes to this, so these two are homotopic and these two are homotopic. And that's the formal definition of homotopic. And as you can tell, this is a really cumbersome and frankly kind of awful definition.
It sort of obviously shows that they're that it's an equivalence relation, though, right?
What's that?
It very clearly shows that this is an equivalence relation.
It does very clearly show that it's an equivalence relation, yes. Right, because they're just the connected components of the looped path, and their connectedness is being in the same component is certainly an equivalence relation. And that's me basically saying the same thing, right? If there's a path from F to H induced by homomorphisms, and so we can see some of the examples of that here. And so one of the first things we did while we were working on this stuff was to try to make this more actually manageable. And so we came with this idea of a spider pair. So two morphisms from F to G to H, and really they can be functions, but we're really concerned with morphisms. Our spider pair if they agree on all vertices except for one, basically. And if two vertices are a spider pair, then they are homomorphic or they're homotopic to each other.
The equivalent symbol means homotopic?
Yes. And so again, here, looking at this example here, right, the only, if this is F and this is G, then they only differ by moving where one goes, right? They agree on 0, they don't agree on 1, so shrinking that leg in is or sticking it out, that's a spider pair. And we can see, right, they're homotopic, right, by the formal definition. And so we gave, here we have another example of a spider pair. If I take a path and I map it into H this way versus this way, they agree on everything but 2, right? So that's a spider pair there. And so one of our favorite results and the most useful from our previous paper that has been accepted by Journal of Algebraic Combinatorics is this thing that we call the Spider Llama, which is that basically given any pair of homotopic morphisms, there's a finite sequence of spider pairs moving from one to the other. And when we were writing this up, we called these spider moves. And the image we had was that G was sitting like a spider on top of H. And every time it like moved a vertex, it was like moving a leg. And so like it was a spider tromping across H is the image that we had.
And this is finite even if the graph is infinite?
That's correct, yes. Because it has to be a path in order between the two morphisms originally to be homotopic, right? That path has to be finite.
Okay, so when you say path, it's finite paths.
Yes.
Okay.
Right, but because one's a beginning point, one's an end point, in order for there to be well defined endpoints, there has to be finite. And so the corollary to this is that not only do we get an image for what the homotopy is actually doing without having to refer to this awful definition, but we also get to beat things to death with induction because we have a very clean and simple categorization, right, of homotopic. And so if we want to prove something is true for a pair of homotopic morphisms, we really only have to prove it's true for spider pairs.
Now this finite sequence, if you go if you're going from F to G, if you want to go from G to F, are the F naught, F1, F2 related to when you're going backwards?
Yeah, so you can trace the same path back, right? So again, if we think back to an exponential object, if I have a spider path, a path of spider moves from F to G, I can happily just walk the same path back.
You don't have to invert them or anything like that. You just have to reorder them backwards.
Correct, yes. And I have a pretty good example of this coming right up. All right, so here I have a graph H, and I have an inclusion of my length 2 path G into H. And I claim that embedding this way and embedding this way, and we'll just say X goes to whatever 0 is, Y goes to 1, Z goes to 2, for simplicity's sake, that these are homotopic. So I should be able to spider move from this embedding into this embedding. So one thing I could do is move over, right? That's only, that differs by only one vertex, so that's a spider pair, right? And then another, and I could just keep walking forward like that, right? And
This graph H is the product of G with I4, right?
Yes, although that's a coincidence.
Okay, no, I'm just saying this is like the when you give someone an example of a homotopy topologically, that's what you do, right? You say the bottom slice and the top slice of the product are
right. Exactly, that's right. So if I reordered it more, right, then this can be a bottom slice and this could be a top slice. That's right, exactly. And if I walk it back, that's the reverse to show, right, the reverse homotopy. And then one thing I have done for fun is I have animated this just so that we can see our spider walking back and forth, right? And maybe this also helps explain why we call these things the spider moves and spider pairs.
Have you counted these things? Can you come up with an object where the path is unique?
Where the path is unique. I'm certain that if your example is small enough, right, that your path could be unique. So maybe something like if your target graph H were a longer path, maybe, and G instead of being length 2 was length 1, the only thing you could do is flop over, right?
Yeah.
And then your path would be unique, yes. So it's pretty clear here that our path is not unique, right? That you could spin around and do all sorts of stuff. There's a ton of embeddings from G into H. I'm fairly sure they're all homotopic because I can I can move this enough so I can spin it around and walk it back. And I'm fairly sure, I haven't checked it obviously, but I'm fairly sure all of the embeddings are homotopic. But you're right, you can come up with examples where it would be unique. And so the last bit of background we wanted to fill in was translating some of our topology ideas into graphs. And so we have this idea of what a fundamental group or fundamental groupoid looks like in topology, and we have two basic ideas for a fundamental groupoid. One is that if I take a walk and I operate that with another walk, what I get is the extended walk, right? Whether or not the walks begin at the same base point or not, right? This is the idea of the operation. If I take a walk and I walk it backwards, that's supposed to be the identity action. And then if I have two homotopic walks, then they should be the same. Oh, excuse me. Okay, am I back?
Can hear you but not see you.
Okay.
See the slides.
I bumped a chord. So share, okay, start video, and then share Acrobat Pro.
Space.
How's that? Are we back?
Yeah, we're back.
All right, great. Oh, sorry about that.
Okay.
And so what we want here is the sort of equivalent ideas. So we have a groupoid, a graph, or a group. Either way, our operations concatenation, so that we have two walks, we can connect the walks, and then you get the resultant walk as a result. We have a process that we call pruning, which is if you take this walk and then you walk backwards, right? Then on each step we cancel, right, the front and forward and back, and that gives you the null action. And then we have two walks here that are homotopic, right? Because I can spider this vertex to this vertex, and that gives you those should be equivalent. It should be homotopic row endpoints. And so if we just consider walks under the first two rules without the homotopic equivalence, then that gives us something we call the discrete group or the discrete groupoid, depending on whether or not you want to start or end at the same base point. And then the addition of equivalence relations on the second condition gives us a homotopic groupoid.
So,
All right.
Tien, does the pruning require there be loops everywhere, or are you asserting this independent of the things we were just talking about?
So here there are not necessarily loops, and so right, it's worth talking for a second on how loops work. So V1 to V1 is not the identity. V1 to V1 to V1 is the identity. Right, so you like do a walk and that's not the identity. But then you do a second walk backwards to kill that walk from it to itself, and that is the identity. If that makes sense.
So I have a question, which is, it seems to me that if I give you a square, right, like a cycle of length 4,
sure,
then its homotopy group is trivial.
That is correct.
That kind of freaks my shit out.
Well, yeah, that's actually going to come up at some point. But you're right. Yes, exactly. We're jumping ahead a bit, but if you take a square, right, then right, a walk all the way around can be spidered into a walk forward, and back, which prunes to the identity. So a square has a trivial homotopy group. It doesn't have a trivial discrete group, right? Because we're not allowed to do the spidering.
Do these walks have to have at least one vertex in common to be able to operate them together?
That's right. So the endpoint of a walk has to be matched with the starting point of the next, starting vertex of the next, right? In order for the operation to find.
For all of them.
For all of them, that's correct.
So what about the homotopic?
Yeah, so it's relative to endpoints. So you're not allowed to spider around the start or the endpoints of those tops. Of those walks, sorry. All right, and so far I haven't said much about covers. And so we'll talk about some of the background of what's known about covers and universal covers in graphs.
Actually, we had a question.
Sure.
Paul said that he was struggling with seeing where the non-trivial homologies arise. So we just talked about how the square is trivial. Do you have a contrasting example that's easy?
Sure. We can go down to, let me see.
Lana says a bigger cycle would do it.
A bigger cycle or a smaller cycle. C3
okay.
would do it too.
So what determines us, like, whether that cycle is trivial? I mean, has trivial homotopy group, like.
So this isn't. It's not in these slides, but one of the results that we showed was that the homotopy group. It's a homotopy invariant. And so if you can find a, if you can basically identify that the graph is homotopy equivalent to something that has trivial homotopy group, then it'll, if and only if it has a trivial homotopy group. And a quick way to find representatives of homotopy classes in graphs is folding one vertex into another. If the neighborhood of one is contained in the other, that's a perfectly good endomorphism, which is homotopic to the identity because it's just moving the one vertex. And so you can just fold a vertex down as much as you can. Right, so can anyone see my my K3 here?
Yeah.
Right? And so, right, if I take a walk like that, right, there's nothing, first of all, there's nothing to spider, right? There's nowhere I can move these two vertices here. Right, these two vertices are pretty much stuck where they are. And then the other thought then is that there would be no place to spider them to, right? Because, well, in this case, a K3 doesn't admit any endomorphisms that aren't automorphisms, right? So, right, they pretty much just got to be where they are. And so the fundamental group or the homotopy group for K3 would just be Z, right? You have your walks, and then you have your walks going the other way, and that's what you get. All right, does that help?
Yeah.
All right, I'm gonna stop this share.
Yeah, thanks for that.
Oops. And so Dana Nguyen was the first person to formally give the definition of covers of graphs and universal cover of graphs in a computer science paper in 1980. And she had a conjecture in this paper that was proved by Tien in 1982 that I'm not going to say what it is just yet, but we'll get there. We have our own proof of said conjecture, which we think is pretty nice and an extension of it. And so one of the reasons why we're going to go through some of these things is in the paper, there was quite a few claims, and latent papers as well, where they just said certain things were obvious. And I'm also not 100% sure that they are as obvious as they said they were. I mean, they weren't hard to prove, but it's worth thinking about for a second. And another reason another thing we're going to go through some of these, another reason we're going to go through some of these is their approach to these topics was very, standard combinatorial and not very categorical. And there were things stronger than what they were claiming that was true, that could have also simplified like a lot of the way one can think about these covers if you try to describe these things in a categorical sense rather than just the straight up combinatorial properties. And for example, there's never any proof that the universal cover is actually universal in any categorical sense, which seems like a oversight, right? If you're going to call something the universal cover. Now, I do get where the definitions come from, because what you get when you do this stuff is something that looks a lot like a lot of the things I'm about to show you look like examples in Hatcher. And it got to the point where at one point me and Laura wondered, are we doing Hatcher exercises? Because like if that's cool, then sure, that's like fun and great or whatever, but I don't know that I could publish that or anything, or anyone would care. And so the answer to that is we're not merely doing Hatcher exercises for the following reasons. One, well, a path in graphs is very similar to a path in top, but fundamentally a continuous function and a group morphism, or sorry, a graph morphism are very different things. There's a graph structure, right, which topology ignores. So like C3 and C4 are very different graphs, but topologically you couldn't tell the difference between C3 and C4. And finally, of course, the homotopy looks wildly different, right? What we're describing as homotopy versus what's homotopic in top. And so for all of these reasons, we are not just about to be doing Hatcher exercises, no matter how much it might look like it at first. So, and then because we're in this intermediate break, here's a picture of my son for no reason. So that's the kid who was mean to Laura. All right. And so what we have as a definition for cover is a graph along with a morphism that's surjective, that's onto, and so that it induces a bijection in the neighborhoods. So if you have a vertex in the codomain with a bunch of neighbors, is for every one of its vertices in the pre-image, there's a bijection between the neighborhoods.
So neighborhood means just the adjacent.
Correct.
Vertices.
Just the vertices that you're adjacent to. So here, for example, we have our G, ABC, and its cover, this thing, C9. And so every time I lift A to A, and F is just going to map AI to A, and BI to B, and CI to C. And so if I lift A to A1, then we see that B and C are its neighbors down here, they're its neighbors up here, and same for the other A's, and then clearly everything holds for B and C as well. Right. And so that is a cover, this graph along with this morphism. And so one
Go back for a second. Let me digest this a little. In your definition, where do you define that G tilde?
Sorry, could you say that again?
G tilde, the G with squiggle. in the definition, you say G, the G be a connected graph, and then you start talking about G, G squiggle, G whatever, I don't know.
Yeah. So I have a hard time hearing.
Okay, so in that definition, you're talking about a graph G, and then
Right.
when you define that function rho, you
Right.
talk that it goes from a G tilde, G squiggle, whatever you want to call it,
Right.
to G. But what is G tilde?
G tilde. So the G tilde is the domain of the graph morphism, right? In order to be a graph morphism, you need a domain and codomain graph. So G tilde is going to be the domain on which this f is going to be defined. And actually, yeah, this should have been a row, not enough. Sorry.
So like in top, right? A cover is a pair. It's a space
Yeah.
together with the projection map.
Correct. Yes. So in this case, the projection, the cover is the G tilde with f or row or whatever.
So you're projecting one into the other using a rule that satisfies a condition.
Correct. Yes.
Okay.
And so, one of our first results is that if I have a walking G, that it lists uniquely to a walk in G tilde relative to my choice of preimage. So if I have a vertex, a blue vertex that's covered by this arrow here, depending on which one of these blue vertices I lift to, any walk starting at this blue vertex has to lift uniquely to a walk up here relative to that. So for example, if I go from blue to red down in G, you have to go from blue to red. Up in G tilde, there is no choice, right? So if I do that, then that's the only choice you have. And then the next step is green, then green is the next step, back to blue, back to red, and so on, right? Any walk has to lift uniquely. And so we get this lovely sort of picture here. And so now we are going to define the universal cover. The universal cover of G is going to be, in our language, its vertices are going to be pruned classes of walks. So if we think back to the discrete groupoid, it's going to be all of the walks starting at V that minus any pruning. So you can't go out and come back, right? Those things cancel. So it's all the walks that up to pruning, and then two walks are equivalent, or they're adjacent, if there's one step from one walk to the other. So if one walk is an extension of one or a step back of the other, then they are adjacent. So let's say I have this graph ABCD as such, right? Then starting at A, AB, AC, ABC, ABCD, ABCA, right? These are all of my walks here, and they're connected if there's a step, right, in between those walks. And then I can walk backwards and I get this thing here.
Okay, you're going too fast.
Sorry, so A is so the null walk or the trivial walk is a vertex here, right? AB is sort of the next walk in this direction, right? Then ABC is the next walk in that direction. And at the point ABC, we have like a choice, right? We can go up to D, or we can go back over to A, right? That's where our choice is from C.
Are the degrees preserved?
Yeah, so that's a result, right? That's not part of the definition, but it turns out that they are, right? Because you get a neighbor for every step you could have taken down at the G level.
What
And
makes
so
it, what makes it universal? Is it unique? Is it the unique graph that covers the one below? Or?
So yeah, so that's a result coming up, right? So we're calling this thing universal, and this is not our definition, although the notion of pruning classes are. They have Angluin used a definition that's similar and essentially equivalent. But right, they didn't define as universal, but that's a result of ours that's forthcoming. But I just want to point out here, like if you're at D, right, what choices do you have as far as another walk goes? Just back to C, right? And the walk A, B, C, D, C is prune equivalent to A, B, C because the C, D, C kills itself, right? And you're just left with the A, B, C. So that's hence this action here.
So this construction really reminds me, like actually if you go in Hatcher, right, and he constructs the universal cover, right, assuming semi-local simple conductivity or whatever, and that's exactly, so somehow the fact that it's discrete means you're not got to worry about that, but it's the same construction, right?
Yeah, it's the same. Right.
You can fold that graph on top into the one below if you're using the same move.
That's right. Yeah, right, and so to address Andrew's point, yes, this is about when we were wondering if we were doing Hatcher exercises, right? It's when we were working this out. I'm like, oh,
there you're going into a hole in my training where you say hatchet exercises. Hatchet, what the heck is that? Sorry.
Oh, sorry. So Hatcher is the sort of standard algebraic topology text. It's where we would be talking about universal covers and covers for topological spaces. And so if you had a topological space, which is like a circle, and that's one with like a little thing sticking out, then its universal cover will very much look like this.
Okay.
Right? And so, right, there's some, certainly a lot of similarity here.
Thank you.
You're welcome. And so this is part of what makes it universal. And so we can factor if you have what we're going to call rho, the map from U to G. Sorry, if I go back, is we're going to take walks in U and map them to their endpoint. All right, so each of these is a walk. We just take them to their endpoint. So ABCD goes to D, ABC goes to C, etc. If we take that walk and you have a covering map from G total to G, then again, for every pre-image of V in G total, there's a unique cover from U to G total that lets this factor. So U covers the covers, basically. So that's not all that's said in this lemma. This lemma just says that this function or this morphism, rho total, exists. And the proof of this is very straightforward at this stage. We know that all the walks in G lift uniquely to walks in G total. So if we have a walk in U, we just send it to whatever its endpoint would have been in G total. And so we have a nice picture of that here, right? I have a walk in G, which corresponds, of course, to a walk in U, which lifts to a walk in G total.
Does the universal cover of a graph cover every cover of it?
That's right. And that's the next theorem, right?
Oh, okay, sorry.
Well, not the next theorem, sorry, but it's on this page of theorems, right, that G is connected. First of all, this endpoint map is a covering. This rho total is a cover. And so the corollary of that is the universal cover is actually universal in the sense that it covers the covers, and it does so canonically, and that's important too, right?
The word canonical here meaning
That there's a unique
way of covering.
yeah, exactly. Yes.
So, for example, there you had a cycle. So cycles are always covered by an infinite path.
That's correct. Yes.
And does anything else get covered by an infinite path or only cycles? Things like that. Can one?
Oh, sorry. I was trying to go backwards. Well, I'm not sure about what sort of infinite graphs might be covered by an infinite path. I believe it would still have to be an infinite path. As far as finite graphs go, you'd be looking at graphs whose connected graphs where every vertex has degree 2. So I would think that's cycles.
Okay, yeah. If it's connected, that's a cycle. Thinking about trees and things like that, if there's a way of using these things to categorize kinds of graphs, I'd be interested to create an equivalent relation on the set of finite graphs by their covers.
Say that one more time, Ramon.
So, you know, one of the things is to like take and classify graphs in a certain way. So you could classify certain set of graphs by their universal cover. You could say all of these guys are equivalent to each other in a sense.
Yes. Yeah, that's right.
Because they don't cover each other. They're covering only goes in one direction, but they're all covered by the same thing. So I wonder if, for example, all trees are covered by the same graph, or there are ways of differentiating between trees.
So all trees are covered by themselves, that they are their own universal covers. And that's because you only have but so many possible paths that are prune equivalent. At some point, you hit endpoints, you hit leaves, and you have to start backing up, right? So the universal cover of trees, if you fix a starting point, they're all isomorphic to themselves.
And if you add an edge to a tree, then that becomes what's called a unicyclic graph. Are those?
So once you have any sort of cycle and not a tree, then all sorts of funny stuff could happen, right? Then you could have that cycle would lift up to like a path, and then you'd have stuff sprouting off everywhere. But
so like
I was wondering, yeah, excuse me, yeah. What would it look like if you just had 2 cycles, maybe separated by something? What would the universal cover look like?
The disconnected graph, you mean?
No, like 2 cycles linked like this, or
yeah, right.
Oh, okay.
So I have a picture of this later in my slides, but you get something that's this weird fractal, like at every time you hit like the intersection, you get to shoot into 2 directions. You can continue along the one cycle, or you get to shoot up, and once you shoot up, then you get sort of an isomorphic fractal copy of the original thing, and you hit back around, and it
Weird.
comes back around. Yeah, there's a picture later.
Okay.
Are all the covers, universal covers by necessity, symmetric in a sense, like fractal in what you were saying, that they repeat themselves because they have to be able to be folded into the same structure, or?
Correct, and not just that, but because if you take a vertex and you walk around your graph and you come back to yourself, then everything you could go, everywhere you could go from there is also everywhere you could have gone originally, right? And so you necessarily get a self-replicating pattern that way.
Okay.
I mean, I think isn't that exactly what you're about to say with the deck transformations, right? I mean, the point of the universal cover is it's got a big group acting on it, right? I mean, in top. I don't know about in graph, but I think that's what you're trying to say.
Exactly. And so the deck transformation is the same way. So in top, the deck transformations will be homeomorphisms from the covering space to itself, right? That preserve that preserve the cover, and in graphs it's just an automorphism, right, of the graph. And so just looking at this, right, in order for, like, all the walks that have to end in A have to end in a walk ending in A. So I can map A, for example, to ABCA, or to ABCA, ABCA, or back to ACBA, right? I can shift it along, but, and then shift the rest of the graph with it, right? Or I could reflect the graph. That's an automorphism that works as well, right, around this. But right, you get the symmetry, right, which bears out in what we were just saying about sort of self-replication. And so I'm just going to summarize like this slide here. The deck transformations are totally classified by walks that start and end with themselves. So every deck transformation can be expressed as precomposition with a walk, or pre-concatenation with a walk. You just take a walk and you stick it in front of the existing walk. And not any walk that starts and ends with V, if I do that, is a deck transformations, and all deck transformations can be expressed that way. And so it's isomorphic then to the discrete group in graph, right? The walks that start and end with themselves. And so the quotient graph is where I take, so I've only defined it for the universal cover here, but you can define it for any cover. You take a group of deck transformations, you take its orbits on the universal cover that it's acting on, and those are your vertices, and you have an edge if there's an edge between elements of the orbits, any elements.
So Tien, if I could jump in here for just a second, we want to be mindful of everybody's time and try and wrap up by
Sure.
4 o'clock here. Is there one or two more slides you want to go through, or go ahead?
Okay, so let me get to the punchlines then. The punchlines are all covers are the universal cover mod some deck transformation. Engluin had a conjecture that if you had if G had X and Y as finite covers of G, then there was a finite common cover of X and Y. And there was a very long technical paper by Layton that proved it, but really, once you do this deck transformation stuff, just mod by the intersections of the deck transformations. And boom, it's like right there. So it's a known result, but it's a very slick way of proving said known result. But the sad part is that homotopies don't lift for the standard universal cover the way they would in covers in top, right? Because here I have these two homotopic walks, row endpoints, and they're not homotopic row endpoints in the lift. So in order to fix that, you impose a condition where it lifts, instead of neighbors, it has to lift like a neighborhood of order 2 or walks of length 2 away, and you have to share endpoints. If you require that condition, then you can lift your homotopies. That's a necessary and sufficient condition. All of those are also covers in the standard sense. You can lift homotopies of functions. You get a homotopy universal cover, which does everything we dream and hope of. And the fact that it is also standard cover means we get to recycle a lot of the results, right, that we just did, which is super nice. And you get the homotopy cover by taking a universal cover and modding by walks that are null-topic, which are equivalent. And yep, A, B, C, B prime A in this graph is that C4, which is null-topic, like Andrea observed earlier. And so there is also a finite homotopy cover, just like there was a finite regular cover if you have mutual homotopy covers. And I have lots of animations here that I would have showed, as well as important questions to be posed. And so yeah, there we go. So, and again, thanks to Stephen, TJ, Brian, Drew, Kate, Laura, Andrew, and Ramon for chiming in and being the audience, and all the math Twitter people that continue to be like the very best supportive math community that I've ever been a part of, at least. And yeah, thank you.
Bravo.
That's really cool.
It's real deep. And that sandwich looks horrible. Anyway.
Well, this is at the very least an honest to God sandwich.
There is nothing holy about that.
So we can take some more questions here in just a second. But before we do that, I want to do a quick advertisement about next week's talk. So I believe next week's speaker is Claire Merriman. Is Claire still with us?
Hi, I'm here.
Do you want to give us a 30-second abstract of what you're going to share with us next week?
Yes, so we will look at billiards on the hyperbolic plane, which is not a normal place to play billiards, and somehow continued fractions will appear. That should have 30 seconds.
All right, sounds great. Thank you.